about the atomic radius. These are two nuclei. You can see nucleus number 1 and nucleus number 2. So atomic radius is the distance from here to here. Okay, this is the radius. So usually we can't find atom individually. So that's why, if, for example, if this is hydrogen and this is another hydrogen, if you have two hydrogens here with you, so it's an H2 molecule actually, H2. So the distance between these two is taken completely, and this distance is divided by 2. Distance is divided by 2. Distance between these two is divided by 2, and you get the atomic radius. Okay. So radius is the distance divided by 2. This is first of all to understand it. Now if you have the atomic radius and you are moving across the period, what will happen to it? And if you are moving down the group, what will happen to it? So atomic radius across the period is decreasing, and down the group it is increasing. Right? Are we clear with this part?
Yes, sir.
Okay. Now you can see here the atomic radius. A graph is given to you about the atomic number and the atomic radius. Now you can see, starting from sodium, magnesium, aluminium, we are going across the period, and you can see there's a fall. Okay, there's a decrease in it. So you will be provided a graph related to that, where you are going to study that graph. Then we are having lithium, beryllium, boron, again across the period. There are little deviations in it, but overall there's a decrease in it. Okay. Now you can see the number starting from, if you start from here, you can see there's a fall, and till here there's a fall, and if you just let me change the color. If you just see here, there was a fall till here as well. So there is a decrease and there is a decrease. Do you have any question? Question will be, why is this so? Whether for across the period or even for down the group. Okay. So why there is a decrease in it across the period? So if we move on a little bit more, which I want to be, this was across the period, right? And down the group also, the same criteria is applicable. Down the group, the atomic number is going to be increasing, not decreasing, but increasing. Okay. Now what's the reason for it? The reason for this is that when we are moving across, we see that the shell is constant. There is no extra shell added across the period. Okay. Moving from sodium to magnesium to aluminium to silicon, phosphorus, sulfur and chlorine, we see that the shell is constant. Okay. So when the shell is constant, it means that there is nothing to be worried about. Okay. If the shell is constant, so you're just adding electrons, nothing else. You're just adding electrons. In sodium, outermost shell 1 electron is there, magnesium 2 electrons are there, aluminium 3 electrons are there, silicon 4 electrons are there, phosphorus 5 electrons are there, sulfur 6 electrons are there, chlorine and argon 8 electrons are there. So the shell is constant. Consider this shell to be stretchable. Okay. You are tying up this with one string, with two strings. What will happen to this? The stretchable shell is going to be compressed. So it was like this with one electron. Now with two electrons, the shell has been shrunk actually from here to this size. Okay. If you will be having 3 electrons, then definitely the size will be reduced because all the stretching bonds are connecting it. So it's just like a rubber band. It's coming inward actually. The more the electrons are there in it, the more it is moving towards the nucleus. Because nucleus is positively charged, the electrons are negatively charged. Okay, so let's suppose if I'm picking up the nucleus of sodium nucleus is having 11 protons in it. Okay, and outer electron is how many? One electron is there outermost. So 11 is attracting 1. Okay, so plus 11 charge and minus 1 charge. Force of attraction, let us compare between the force of attraction of chlorine. Chlorine is having 17 protons in it and 7 electrons in it. Okay, so force of attraction between 17 is more attraction as compared to this one where the attraction is less. Okay, so that's why the size is bigger for it because less attraction is there, and the size for chlorine is smaller, and we call this as the atomic radius. Any question you can ask me, please. Is there any question? No, sir. Okay. So let's move forward. Melting and boiling temperatures. Melting and boiling temperatures, you can see tabulated information is given to you. Lithium, we are moving now. Beryllium, boron, nitrogen, oxygen, fluorine. Okay, so we are moving across once again, and we need to see what is happening. Carbon is there, oxygen and fluorine is there. See the melting temperature here. Melting temperature is slowly and gradually increasing. There was an increase till here, but after that you can see negative. Then in the negative you are going towards more negative. So from lithium, beryllium, boron, you are dealing with the metals, metallic, then you are working with the bonding type covalent and covalent, but these are macro. Okay, macro covalent or giant lattices. You can see giant metallic lattice, metallic is strong, giant metallic lattice, giant covalent, strong one. The stronger the lattices are, more energy is needed, so that melting temperature and boiling temperatures are going to be high. And for nitrogen, oxygen and fluorine, simple molecular structures are there. Simple means weak force of attraction are there. So covalent bond is there, but the force of attraction are weak. That's why you can see that the melting and boiling temperatures are lower. Okay. Period number 3, moving from sodium to magnesium. See this: aluminium, silicon, phosphorus, sulfur and chlorine. Now you can see it was 98. Even the boiling point, focus on that also. It's 883. So you can see there's a slight increase till here, and then there's a fall. Now especially focus on this. There is a fall. For fall I'm just showing this arrow, and then there's a rise, and then there's a fall. The examiner will ask you this question also about this specific area. Okay, so if I'm trying to show a graph, the graph will be like there will be a rise on the graph for this melting point, rise till 1400, then there will be a fall, then there will be a rise, and there will be a fall. So you'll be facing a graph like this. So the examiner will ask you that why there's a fall and why there's a rise in it. Now if you focus on the structure, metallic, okay, giant lattices, so definitely we understand that the giant lattices are having strong force of attraction. Then we have the covalent character, and giant lattice is there, stronger force of attraction, high melting and boiling points. Simple covalent. But why there's a difference? Why there's a fall and then there's a rise and there's a fall? It should have been like the previous one. There could have been a fall and a fall and a fall in this one, right? There was a fall, regular fall, but in this case it's not like that. So we need to explain that. Are you ready for that? Shall I start explaining it?
Yes, sir.
Okay.
Yes, sir.
For the intermolecular forces, keep this in your mind that the intermolecular forces in the non-metals, they depends on the number of electrons. Okay, the more the number of electrons, the stronger the intermolecular forces. Okay, intermolecular forces mean the force of attraction between molecule A and molecule B. Okay, so if molecule A is having more electrons and molecule B is also having more electrons, then this force is very strong. When the force is strong, then the boiling point is high. Okay, this is a concept. Shall I move on? Shall I keep working on it? Are you with me?
Yes, sir.
Yes, sir.
Okay, now I want you to listen to me very carefully. This is very conceptual, that's why I want you people to be listening to me carefully. Okay, now focusing once again on this. Phosphorus. I want you to focus on phosphorus, sulfur and chlorine. These three only, and I'm giving you the explanation for that. Phosphorus is existing as P4 molecule. Okay, one molecule of phosphorus is P4. So force of attraction between one P4 and another P4. We will see this one. Sulfur is existing as S8, one molecule. So force of attraction between one S8 and another S8. We'll see this. And chlorine is existing as Cl2, one Cl2 with another Cl2. We'll see this force of attraction as well. Are you with me?
Yes, sir.
Yes, sir.
Phosphorus, we need to see the number of electrons in phosphorus. So phosphorus is in the group of nitrogen. Okay. In the group of nitrogen, I want you to open the periodic table and tell me the atomic number of phosphorus and the atomic number of sulfur and the atomic number of chlorine. Atomic number for phosphorus is 15. I'm talking about the atomic number. Okay, atomic number is the number of protons which is equal to the number of electrons. Okay, so times 4 times 4, I'm calculating electrons. 16 times 8 and 16 times 8. 17 times 2, 17 times 2. 60 electrons are attracting 60 electrons. Now the word I'm using, attracting, it seems to be strange. Why electron is attracting another one? The reason is that if one electron is spinning clockwise, the other electron will start spinning anti-clockwise, and then only the attraction is possible. Okay, so there the force of attraction between these electrons, we are going to compare it, and then the force of
Again?
yes please.
So can you explain again?
I'm telling you that the number of electrons here are going to be showing a force of attraction with the number of electrons here. Why they are attracting each other? Because if they are spinning clockwise, these electrons will start spin anti-clockwise. So force of attraction will be generated. If this is positive, then this will become negative. If this is south, this will become north. Okay, so then a force of attraction. So these two molecules P4 and P4, an intermolecular force of 60 and 60, and here the intermolecular force, how much is there? 128 and 128. Now we are comparing force of attraction and then 34 and 34. Now see, 60 and 60 attraction is less as compared to 120, 128 extraction, force of attraction. So that's why the force of attraction which we have seen here in this case, phosphorus, and in sulfur and in chlorine, why the pattern is like this? Because sulfur is having more electrons, more attraction is there, more electrons and more attraction, while chlorine is having less number of electrons even as compared to sulfur and as compared to phosphorus. That's why the graph is, first of all, if this is sulfur, if this is phosphorus, then it is rising up and then going down even more than phosphorus. Why chlorine is going more than phosphorus? Because you can see the number of electron present in front of you. 34, 34 force of attraction is less as compared to 60 and 60. And sulfur is of no comparison because it's already having a high number of electrons as compared to both of them. That's why sulfur stands here. Clear?
Yes, sir.
Yes, yes.
Okay, this video will be uploaded on the YouTube. Okay, if you miss anything, you can watch it again with the same everything. Okay, the screen will be available to you. Okay, now moving a little bit forward, and when we are moving a little bit forward, then we reach to. Okay, if you have any question, you can ask now. Do you have any question?
No, sir. No.
Okay,
No, sir.
so I'm moving towards the ionization energy now. And moving towards the ionization energy is, what is ionization energy first of all? So we need to know the definition. Okay, when we are defining something, ionization energy, you might be knowing about delta H. What is delta H?
Sir,
Change in temperature.
Sir, enthalpy change.
Absolutely. So this is the enthalpy change. Now ionization energy is actually the enthalpy change. Okay, when I'm defining ionization energy as an enthalpy change, you see that there are certain look here, there is a sign here on it. This sign is called phi. Okay, mathematical sign phi, or people call it sigma as well. This stands for STP, which means standard conditions of temperature and pressure. Okay, what are those standard conditions? The standard conditions are three. Standard temperature, it is 398 Kelvin, 298 Kelvin, sorry, 298 Kelvin, and pressure is 1 atm. Okay, so when I'm using 298 Kelvin and 1 atm and I'm calculating enthalpy change, it is considered to be the standard enthalpy change. Okay,
Sir, 298 Kelvin is room temperature.
it's 25 degrees Celsius room temperature. How to convert 25 into 298 is C plus 273 will give you the result of Kelvin. So C is 25 plus 273 and you get 298. Clear?
Yes, sir.
Okay.
Yes, sir.
Now, I'm coming towards ionization energy. So I'll be using enthalpy change word when I'll be defining it. Okay. Now I'm going to write one equation for you and this equation will give us an idea how the ionization energy can be defined. Okay, because questions based on certain equations are also being asked. I'm writing one equation for you. I'm writing sodium plus one, sorry, sodium is losing an electron and changing into sodium plus 1 with one electron being lost. This is in the gaseous state, this is all in the gaseous state. Okay, how many moles of sodium are there?
1.
1 mole of sodium, 1 mole of sodium, and 1 mole of electrons are there. So everything is 1 mole. And if this reaction is happening at STP, then the first ionization energy can be explained from this equation. 1 electron is lost, that's why it is called first ionization energy. So how I'm going to explain this now? Standard conditions, STP and 1 mole. Keep in mind. So I'm using the word, now see, listen to me how I'm doing it. The enthalpy change for 1 mole of sodium gaseous atoms to be converted into 1 mole of sodium plus 1 cation by the release of 1 electron, 1 mole of electrons, by the release of 1 mole of electrons. Okay, this is called first ionization energy. Are you clear with this?
Yes. Yes, sir.
Actually, this is the amount of energy, okay, which is released out or which is needed actually. So when I'm using the word enthalpy change, it means that I'm saying I don't know about the release or needed. That's why I'm using the enthalpy change. Enthalpy change is giving you a cover, okay. You don't know whether it's exo or endo, then use the enthalpy change. So the enthalpy change for 1 mole of sodium gaseous atoms to be converted into 1 mole sodium, I'm defining it from here, from the equation. Okay, so let me do it once again for you. It is the enthalpy change for 1 mole of gaseous sodium to be converted into gaseous sodium cation by releasing 1 mole of electrons under STP. Are we clear with this?
Yes, sir.
This is the ionization energy. Now we are going to compare and see the first ionization energy of all the elements across the period, right? So we are going to see it, what is happening there. So there's a graph given here right in front of you. You're going to focus on that graph and see how we are doing it. Look at the graph now. The graph is hydrogen losing 1 electron and helium losing 1 electron. You can see there is a rise between hydrogen and helium. The reason for that is that when we talk about hydrogen, it is 1s1, and when we talk about helium, it is 1s2, right? 1s1 means that you are eliminating 1 electron from hydrogen, which is free electron. And 1s2 means that there are 2 electrons in helium. So it is completely filled. So we have a concept of half filled and completely filled. If we compare half filled and completely filled, which one is more stable? The completely filled is more stable, right?
Yes, sir.
So to remove 1 electron from half filled is easy as compared to remove 1 electron from completely filled. right? So this one needs more energy and this one needs less energy. So this is for hydrogen with less energy and this is for helium with more energy. Are we clear?
Yes, sir.
Okay. I'm going to stop it here now because if I go further explanation, then maybe you'll get confused into it. I want you to please go through this conversation and this discussion again and again. It will be on my channel, so you can download the video from there and you can watch it or watch it there again and again. This is very, very important. That's why I'm stopping it here because if I give you more concept about this, I'll be explaining this graph tomorrow, inshallah, as well. Okay. So, any questions?